With the continuous development of technology, smart cities have entered a new era. Among them, intelligent transportation systems based on unmanned aerial vehicles have become an indispensable component of the Internet of Things in smart cities. Compared to traditional logistics, unmanned aerial vehicles, UAVs, operate in the air with a short transportation distance. The use of UAV technology for logistics distribution can enhance the efficiency of distribution. In addition, UAVs can also reduce labor costs by allowing logistics companies to use fewer workers. The development of reinforcement learning provides a new method for intelligent cooperation of UAV swarm. However, these methods are resource-intensive and cannot be directly applied to UAVs where computing and storage resources are limited. Secondly, if we use distributed UAV-level devices to train deep reinforcement learning models, the training speed may be unacceptable due to inefficient data acquisition. Thirdly, using UAVs to collect data directly in the real environment is prone to errors. Fortunately, digital twins offer a promising solution. The digital twin network builds high-fidelity virtual models based on expert knowledge and physical models. In our DTN, we can use digital twins not only to build the network topology of physical air logistics network, monitor network parameters and models, but also optimize the strategy policy as well. Therefore, we established a service-oriented UAV cooperation framework based on digital twin network and realized UAVs through DRL method control. The UAV service is abstracted as a cargo order task using service paradigm. By establishing a high-fidelity virtual decision model, the problem of limited computing power of UAV is solved. However, how to apply DT and DRL architecture is still a problem to be solved. In the scenario of UAV logistics transportation, we consider the following two questions: the real-time order allocation and long-time sequence path planning. Due to changes in number of UAVs and cargoes, it is impossible to retain all possible input neighbors and cargoes. The transformer architecture is invariant to the arrangement of input vectors, enabling the UAV to process variable messages during flight. Based on transformer architecture, agents can pay attention to important parts of complex and heterogeneous information. The cargo selection decision of UAVs is set as the upper-level task, and the flight path planning of UAVs is set as the lower-level task. In the latter, due to limited battery capacity of UAVs, we consider the existence of charging stations and divide the task into subtasks of charging and cargo delivering. We designed a square area as a simulation site for logistics transmission. Blue dots represent cargoes scattered in the area. Red dots represent UAV charging stations, and symbols represent UAVs. The size of the blue dots represents the urgency of the cargoes. In the target area, we randomly initialize UAVs in the cargo bin in the lower left corner. The UAV selects the cargo to be carried and flies to the cargo acceptance point. We set the expert strategy as follows. During the selection of cargoes, UAVs select the nearest unselected cargoes. During UAV path planning, the UAVs go to the UAV charging station when the energy is below a certain value. We set the following measures to evaluate the performance of the trained model. We use the average number of successful deliveries per UAV to represent the efficiency. We use the average waiting time of cargoes to represent the fairness of air logistics network. As shown in the figure, with the increase of cargoes, transformer based on hierarchical reinforcement learning yields a better result. SAC HR Trans has an efficiency improvement of 18%. The comparison between SAC MLP and SAC Trans shows that with the increase of cargo quantity, the UAV strategy network based on transformer architecture is more inclined to choose cargoes with a longer waiting time, thus improving the fairness of air logistics network.